In the next section, we'll be looking at molecular orbitals of the cycloadditions. In the molecular orbital that you see on the left, that is the molecular orbital for butadiene, which is this structure, and also of ethylene. The HOMO of 1, so the highest occupied molecular orbital of 1, is going to interact with the LUMO of the other one. The dienophile, which is the alkene, is the electron poor species. That's where the electrons are going to go into the LUMO. So the LUMO will accept those electrons. And the butadiene is the electron-rich species, and the HOMO is going to contribute its electrons into the LUMO. The reaction is therefore initiated when electron density is transferred from one into the other. So electron density flows from the filled orbital of the HOMO into the empty orbital of the LUMO. This is just a shorthand of what I just said. The electron density flows from the highest occupied molecular orbital of the diene to the LUMO of the dienophile. So the 4 of the carbon atoms will rehybridize to give sp3 hybridized orbitals that can form these sigma bonds. So you can see the HOMO of butadiene with the way the electrons are and the one node. So we have these 2 red ones here that are in sync with each other. So we have these blue opposite ones. And then the LUMO of the ethylene, those match up. We have red on the bottom and red on the top here, and the blue, and those come together to form the sigma bonds. If we look at ethylene plus ethylene to form cyclobutane, if we look at the HOMO of 1, just the 2 electrons, and the LUMO of the other, and we look at the molecular orbitals, try to line them up together, they don't line up. This is forbidden. We have red and the blue and the red and red. These 2 line up, but this one doesn't. So here we're not going to form cyclobutadiene. If you want to perform that reaction, however, what we can do is add light, and when you do that, you excite the electron that's in the HOMO. So that there's 1 electron in the HOMO and 1 down in this lower level. When we do that, the electrons now can line up because the phases are in the right spots. Then we can form cyclobutane. In order for us to excite the electron, we need to have light in order to excite the state so that the phases match each other. In an electrocyclic reaction, it's a process where a conjugated polyene can undergo cyclization. These reactions can be reversible, but just like any reaction, there's going to be certain products that are preferred. If I look at the electron movement here, these come down here. So I've made a new sigma bond, and then the double bonds have moved. You can see that equilibrium is preferring the product, so a cyclic structure is preferred. If I move the electrons here, the preferred is the open structure. This is preferred. And that is due to angle strain. In these electrocyclic reactions, the stereochemistry is based on the react conditions. The stereochemistry is based on the reaction conditions as well as the number of pi electrons. So this is going to form a 6-membered ring. And something else that we have to consider is how the CH3 groups are oriented in relation to each other. If I use heat to do this reaction, these will be cis. If I do this reaction under photochemical conditions or using light, my methyl groups are trans to each other. I get this plus the enantiomer. And if I use light with the cis product, that will open up the ring to this compound, and heat will also give that compound. Or this diene here, this new bond is formed. Methyl groups are trans with the light. This is trans with heat, and the light will make it cis. If we have these CH3 groups that are pointing outwards of each other, when the reaction closes the ring up, we get the cis. If one is pointing in and one is pointing out, With heat, you get the trans. And this can be explained using molecular orbital diagrams. So similar lobes are going to react with each other. We can see the HOMO here. This is the two nodes that we see in the highest occupied molecular orbital. And these red lobes line up together. We can see where these CH3 groups are that are pointing outwards, as you see in this first reaction here. And what happens is the red lobes have to rotate in a disrotatory fashion in order for them to come together. So one lobe is going in clockwise, the other one is coming in from a counterclockwise position. So 6 pi electrons, when they are moving in a disrotatory fashion. So if you imagine the red pens are the CH3 groups and my thumbs are the red lobes that are going to interact together, this one has to rotate up this way in the counterclockwise fashion. This one's rotating in the clockwise fashion in order for my thumbs to come together, and my CH3 groups are on the same side as each other. When my CH3s are out like that, my thumbs are down. One is going counterclockwise, one's going clockwise to come together. These groups are cis to each other. So that's the disrotatory. One is going in opposite direction than the other to come together to form that bond. So in the other example on this slide, one methyl group is out, the other one is in towards the ring. So I have my thumbs here. When they come together, that one will orient itself in a trans position. If you have 4 pi electrons, these move conrotatory, which means they're both moving in the same direction. Here we can see the HOMO and the LUMO with the one node. These don't line up together the way the other one did, so these move in the same direction. This one's going counterclockwise. This one is also going counterclockwise. That's what needs to happen in order for those to come together. And the same thing can happen for them to come apart. So if I look at my thumbs here, I have this CH3 sticking out. So these are the red lobes. And when they come together, this one is going counterclockwise. I'm also going counterclockwise here. My methyl groups are trans to each other. So methyl out, methyl out. My lobes are one's up, one's down. This one goes counterclockwise. This one goes counterclockwise to come together, and I get the trans orientation. That's what happens when the reactions are heated. When you use photochemical energy or light to do the reaction, the opposite is true. In this case, the 6 pi electrons with light undergoes conrotatory closure. 4 pi electrons with light undergoes disrotatory closure. So where the CH3s were out before, when you use the conrotatory, one goes down, one goes up. The disrotatory, if you're opening it disrotatory, one's in and one is out. So here is kind of a table that summarizes that. If you have an even number of double bonds under thermal conditions, which is heat, you'll get conrotatory. With the even number of double bonds, photochemical, disrotatory. So this is like etc. E, even, thermal, conrotatory. This is E, P, D. This is like the 4 pi electrons. And the 6 pi, or the 3 pairs of electrons, that would be an odd number under thermal conditions, OTD, and then OPC. All right, so in this example, we have light, we have an odd number, so this would be the OPC, so we're going to do conrotatory. If you can imagine this is conrotatory, the CH2 pH groups, if I have one lobe down and my phenyl is up, one lobe up and the phenyl is up, it's conrotatory, so they're going to be trans to each other, which is the product that you see drawn here. So this one was odd number. It was under photochemical conditions, so this is a conrotatory. So we get a trans product there. So you can attempt to do each of these so that this one is odd. We have photochemical conditions, so OP, that one is conrotatory. Those are both out, so it's going to be trans for conrotatory. So this is my new bond. These will be trans plus the enantiomer. This is involving an even number of pi electrons under P, so this will be disrotatory. So these electrons come out here, and those come there. This one is a reverse one. Double bond, and then these will both be sticking out that way. This one is an odd number, thermal. This is OTD, disrotatory. For the disrotatory, we have one thumb is down, though they're both going to be thumbs down in disrotatory. I have one group that is out, one group that is down. So if I disrotatory to bring my thumbs together, then I get the trans. So a double bond here, single bond, and I said that would be trans plus the enantiomer. In a sigmatropic rearrangement, we get a pericyclic reaction in which one sigma bond is replaced with another one. If I follow the electrons here, this green is showing the sigma bond that's broken. So that one is broken, and I'm going to form a new one there. And these are the pi bonds that were formed. So this sigma bond was formed. This one is referred to as a 3-3 sigmatropic rearrangement. So this had 1, 2, 3, 1, 2, 3, and that's why it is numbered that way. We have the 3 carbons involved and the 3 carbons involved in the rearrangement there. So this right now doesn't look like a useful reaction because you've just essentially flipped it over. But if you had substituents coming off of any of these carbons and they could be moved to a different spot, that is where it could become useful. This reaction here is a 1,5 sigmatropic rearrangement. You can see which bond is being broken there. I'll show you the intermediate. So there's this bond that was broken, this one's being formed, and these are all moving as well. This is 1, 2, 3, 4, 5. So this is the transition state. And in the product, we have this. So the 1 group moves to the 5, hence the 1,5 sigmatropic rearrangement. So before the alkene was on this methyl group here, and now it has shifted away from that. The Cope rearrangement is a 3-3 sigmatropic rearrangement where all the 6 atoms are carbons. So every one of these is carbon. This bond is formed, this one, and this one is formed as well. So this happens in 85% yield. So that's the Cope rearrangement. We also have the Claisen, where it's the same mechanism. The electrons are moving around in the cyclic fashion. One of the 6 atoms is going to be an oxygen here. New bond, double bond, double bond. We went from having an ether, or a vinylic group, and an allylic group, to now this is just a carbonyl, so you can see which one is preferred. And this is the same type of mechanism. We have the allylic group here with a benzene ring. It's going to rotate around so that you can move these electrons around. So it forms this first, which is the ketone on a benzene ring, and we've seen tautomerization before. Usually it's from the enol to the ene, but in the case of this, the benzene is preferred over the cyclohexadiene with that external carbonyl. So that will tautomerize to form the benzene, which is preferred.